my childhood, one of my favorite hobbies was watching space shuttle launches. So this is a huge spacecraft which has two solid rocket boosters and three powerful main engines which burn liquid hydrogen. And it is able to take more than 100 tons of material into orbit around the Earth. Have you ever wondered how do these rockets function? The answer is in this session. You know already that Newton's third law states that for every action or force in nature, there will be an equal and opposite reaction or a counter force. When a rocket lifts up with burning fuel, rockets eject gases in the backward direction, and that creates a momentum of the gases in the backward direction. And by the conservation of momentum, the rocket gets momentum in the forward direction, making it move in the forward direction. Thus, the rocket works on the principle of the conservation of linear momentum. Let's learn more about linear momentum and momentum conservation. To calculate linear momentum, mass and velocity of the system are required information. The formula for linear momentum is P, that is momentum, is equal to mass into V. Just recall Newton's second law. F is equal to the derivative of momentum with respect to time, or dP by dt. So F is equal to dP by dt, where F is the external unbalanced force acting on the particle. Now, consider a system of n number of particles who have masses m1, m2, m3 and so on till mn, and each of these particles has its own unique velocity v1, v2, v3 till vn. The particles may be interacting and have external forces acting on them. So, linear momentum of the first particle p1 is equal to m1 times v1. For the second particle, p2 is equal to m2 times v2 and so on. So, for the nth particle, the momentum is pn equal to mn times vn. For a system of n particles, the linear momentum of the system is defined to be the vector sum of all individual particles constituting that system. So, capital P, that is the total linear momentum of the system containing these n interacting particles, is equal to P1 plus P2 plus P3 up to Pn. Now, summing up all of these individual momenta, we get capital P is equal to m1 v1 plus m2 v2 plus m3 v3 till mn vn. Now, from the above equation, the total momentum of a system of particles is equal to the product of the masses of the individual particles and the velocities of the individual particles. If these particles are moving in unison, we can say that the momentum is equal to the total mass of the system and the velocity of its center of mass. So, the equation becomes capital P, that is the momentum of the total system, is equal to capital M, that is the momentum of the combined system, times V, where V is the velocity of the center of mass of the system. That is, the total linear momentum of the system of particles is equal to the product of the total mass of the system and the velocity of its center of mass. But what is the center of mass? You can imagine the center of mass being a physical point on that object through which all of the mass of the object can be said to be concentrated. In other words, if you apply a force directly through the center of mass, the object will accelerate linearly instead of rotating or turning. In other words, an object will have only translatory motion if the force applied through it is passing through the center of mass. Now, coming back to the derivation, by differentiation, we know that dP by dt, that is the derivation of the total momentum with respect to time, is equal to the differentiation of capital M times capital V. Since the mass of the system is remaining constant, this becomes equal to m times dV by dt. Using Newton's second law, dP divided by dt is equal to the external force Fext. This above equation is nothing but Newton's second law for a system of particles. We know a change in velocity with respect to time is acceleration. So, we can say that dV divided by dt is equal to capital A. So, the equation for the total linear momentum of a system of particles becomes F external is equal to capital M multiplied by capital A. If the total external force acting on the system is 0, Fext is equal to 0. So, dP by dt will also be equal to 0. This would mean that P, that is the total momentum of the system, is constant. So, wherever there is a total force acting on the system of particles and that is equal to 0, then the total linear momentum of the particles will also be constant. The rate of change of momentum is also 0, which means that there is no change in the momentum, which means that linear momentum is conserved. This is the law of conservation of total linear momentum for a system of particles. Let's understand what this means with an example. When we define a system of particles, we can distinguish between internal and external forces. Internal forces are forces exerted by particles on each other. If external forces are zero, then the center of mass moves only due to internal force. So the center of mass moves with a constant velocity, that is, moves uniformly in a straight line like a free particle. Here we consider the radioactive decay of a moving unstable particle. Alpha decay is the nuclear decay process whereby the parent nucleus is emitting an alpha particle. So in this case, it is the decay of radium. The parent nucleus of radium emits a daughter of nucleus radon and an alpha particle as shown in the figure. Now, this is due to internal forces within the parent nucleus. This is due to internal forces in the system, and the external forces on the system are negligible or zero. From the figure, we can see that the decay products of the radon nucleus and alpha particles are moving in different directions, but the net center of mass of the system is moving in the same path in which the decay was originally taking place. In other words, even though the constituents of this decay, the alpha particle and the radon nucleus, are moving in different directions, the center of mass does not change its direction or its velocity. In other words, the original momentum of the system is still conserved. The decay particles move in different directions, but the center of mass of the system remains in uniform motion. What happens when the center of mass is at rest? In that case, after the decay has happened, the total velocity of the system will still remain zero. This can only happen if the sum of the momenta of the alpha particle and the daughter nucleus sum up to zero. Thus, we understand that whether we are dealing with a single individual particle or a system of linked particles, the conservation of linear momentum will hold equally well for both cases. Let's summarize what we have learned so far.
Manorama Horizon. Learning made simple.